Hi there, welcome to my talk. Today I will be presenting the paper Settling the Relationship between Wilber's Bounds for Dynamic Optimality. I'm Victor Lecomte, and this is joint work with Omri Weinstein. This talk is going to mostly be an introduction to the dynamic optimality conjecture and what our results mean for it. This is going to be very, very light on proofs, so I think it will be accessible to everyone, even if you don't have any background in the dynamic optimality conjecture. First part is about binary search trees and the dynamic optimality conjecture. First, a very quick recap on what binary search trees are. There are trees, binary trees, made of where every node contains one key and it follows one simple rule. The rule is that when you have one node X that has two subtrees, everything in the left subtree has to be smaller than X and everything in the right subtree has to be bigger than X. And this one property makes it very easy to find keys, because you can just start at the root, and if the element that you see is too big, you go left, and if the element that you see is too small, you go right. And binary search trees, at least the static kind, are very good for static dictionaries, because you can make them balanced at the start of time, and if you make them balanced, then the depth, maximum depth is going to be at most log n, and that means that any query that you might have will be executed in at most log n time. But can you do better than log n? Well, in the worst case, you can't, because there's always going to be at least one node that is at depth at least log n. But what if one of the keys is queried very often? It would be nice to put it near the root so that it's answered more quickly. In general, we might want to adapt to the kind of queries that we receive. For example, if key 7 is asked very often, then we might want to put it at the top over here. Now, how can we transform the structure of BST? Essentially, we need only one operation, that is called the rotation. The operation goes as follows. If you have a key X whose parent is Y, then you can rotate the edge, joining them to the right so that X becomes the parent of Y. And all of the trees dangling off of X and Y will be distributed in this way. This operation is good because first it is valid, it preserves the BST property that everything to the left is smaller and then everything to the right is bigger. But also it's very powerful because it can help you transform any valid BST into any other valid BST as long as the nodes are the same. And you can do that actually in a linear number of steps in a number of keys. That's a pretty nice exercise if you want to think about it. Rotations can help in many cases, and there's different kinds of structure that you might expect from the sequence, from the input sequence. One is time locality, where the exact same query is repeated many times in a quick succession. For example, you could have the sequence 5, 5, 5, 5, 2, 2, 2, and in that kind of case, you might want to move the key that is being queried to the root. So first you would move key 5 to the root, and then you would move key 2 to the root. Another kind of structure that you might use is space locality, where you don't get asked the exact same key, but you get asked keys that are very close to each other. In which case, one good strategy might be to flatten the whole tree into a single path, and just as you get asked queries, you just pull on the rope in one direction or the other so that you get to the key that you want, and the time that you would have to spend for that is only proportional in the distance between two consecutive queries. Which is much faster than log n if those queries are close together. And those are only two examples of structures, and it might be mixes of time and space locality, or they could be something else entirely that still makes it very fast for a binary search tree structure that is allowed to do rotations. Now, can we get every possible benefit at the same time? That is there a single algorithm that does well against all of those kinds of structures and essentially beats every possible strategy that you might use for those kinds of structures? And it would be a very strong requirement, because you can't really know what the best strategy is in hindsight, because you have to answer the queries one after the other. You have to adapt on the fly. So is that too much to ask for? And the answer is, well, maybe. We don't really know yet. And that's the dynamic optimality conjecture. But first, let's make the question rigorous. So what's our benchmark? What's the goal that an algorithm should be able to achieve? Well, we are given a sequence of queries, which are a sequence of m keys, each from 1 to n, where we assume that m is at least n. So we know the sequence of queries in advance. In the rules that an algorithm to execute x would have to follow is that first it has to start from a fixed initial binary search tree on the set of keys. It might be just the path from 1 to n. It doesn't really matter, because, as I said before, you can easily transform one into the other. What really matters is what happens afterwards. So when you receive a key xi, in order to be fair, you have to start the pointer at the roots. And then what you can do is you can move down, we can move up, you can rotate things along the way. And at some point within that time step, you have to access the node that has key xi, because you have, like, if you're implementing a dictionary query, you would want to, at some point, go to that node so that you can answer the query. And we're going to say that each of those operations costs 1, just a unit cost. And we're going to define our benchmark, OP of x, as the lowest possible cost you might have had while executing the sequence x. So this is very low in a sense, because for the definition of opt of x, you're allowed to know everything about x in advance. But it's still not trivial, as we'll see. So what are some things that we can say about opt of x? First, it has to be between theta of m, which is just the length of the sequence, and theta of m times log n. The reason why it's at least theta of m is just because of the way we defined it. We have a unit cost at least for every query. And the reason why it's at most m log n is because, well, if you just used a balanced binary search tree and you didn't move it at all during the queries, then you would get that time. And it can be seen by counting arguments that you can actually, that there are sequences that do require that much time. And that's the next exercise if you want to think about it. Now, also we don't really care about constant factors, because it's an artifact as a definition. We might have defined it in a way that blows the time up by 2 or divides it by 2. It doesn't really matter. And because of those two facts, because of the fact that we need at least theta of m, and that we don't care about constant factors, we also don't care about additive order of m terms when looking at notions of costs for a binary search tree. So what is the dynamic optimality conjecture? Or what is the general question that we are asking here? We are wondering if there's an online BST algorithm A. And by online, I mean it doesn't know the sequence X in advance. It just receives the queries one by one. So is there an online binary search tree algorithm such that for any possible sequence X of queries, the cost of executing X using algorithm A is at most a constant factor bigger than the best you could have done in hindsight, than opt of X? And surprisingly, there's not just one, but even two candidates for dynamic optimality that are conjectured to be dynamically optimal. The first one is splay trees, which was introduced by Slater and Tarjan in '85. And in that same paper, they already conjectured that splay trees was dynamically optimal. The second candidate is slightly more recent. It's called greedy, and there's been more and more proved about it, and it's probably more likely that we're going to prove that greedy is dynamically optimal before we prove that splay trees is, if of course the conjecture about them is true. But really we have at the moment no idea how to prove it. It's very elusive conjecture. But still, there's been some very nice results, and there's a lot of results that have managed to relates this quantity opt or a benchmark and in general binary search trees to a geometric view. And what I mean by a geometric view is if you plot the sequence of queries over time and you look at the geometric properties of that plot. So we'll call it G sub x. And for a sequence x, like 3, 1, 2, 5, 4, we just plot them a long time. But here time is vertical. That's a convention that's a bit weird, but you get used to it as you work on it. So we just plot 3, 1, 2, 5, 4 in that order. We just plot it a long time going up. I was going to talk about a very nice result that characterizes OPTX using the geometric view, but I'm going to skip it for now for the sake of time. You can ask me about it in the poster section. Now I'm going to focus and I'm going to zoom in on the results that we had in the paper, on the parts of the conjecture that we care about. And those are lower bounds. So first, why would you want to care about lower bounds on OPTX? The reason is that OPTX is kind of annoying to work with, and the reason for that is that all the known definitions for it are the minimum over some large set of things. For example, the original definition is the minimum over all algorithms, over all possible ways to execute sequence X. And in the characterization in the geometric view, it's also the minimum over all sets of points. So in order to prove that an algorithm like split trees matches OPTX, we would need to consider all of those algorithms or all of those sets of points. But it would be very nice if we could have some sort of closed form, because the closed form would allow us to only compare it to one thing rather than having to prove that it's bounded by many things. And the lower bounds that we have, the two very important ones, have been proved by Wilber in 1989. He showed two lower bounds on OPTX. One is the alternation bound, denoted alt, and the other is the funnel bound, denoted funnel. And as far as we knew before this work, at least, they could all have, like both of them could have been equal to opt, up to constant factors. And so if that were the case, then that would give another expression for opts, one that might be more convenient to work with. So I'm not going to go over the definition of the alternation bound for the sake of time. I'm going to switch directly to the funnel bound, which we've studied more intensively. So the funnel bound is a bit tricky to define. So first you have to fix a time step I. So you have to fix if you're thinking of the geometric interpretation, you have to fix a y coordinate I. And you consider the points under that line such that they form an empty rectangle with the axis at time I. So let me clarify what this means. So here you have the plot of x, but you only have it up to I because we don't really care about what happens above it. And you will look at all the points such that the rectangle, so here would be a point P, and you look at all the points such that the rectangle between P and the axis at time I, which is xi comma I in the geometric view. If that's empty, you call it a funnel point, and we illustrate those in orange. For example, this point is not a funnel point because the rectangle here contains another point here. So once you have those funnel points, what you do is you enumerate them going from bottom to top. And you look at the trajectory that this takes. Every time this trajectory crosses the dividing line at x coordinate xi, you add 1 to a counter. And this will be the funnel of x at time I. This is how it's defined. And then the funnel of x overall is just the sum of the funnel of x for all time steps I. Now our results about the Wilber bounds are in line with the popular belief, which was that first, the alternation bound is not tight, second, that the alternation bound is weaker in some way than the funnel, and third, that the funnel bound is tight, that is, that the funnel bound matches opt. So before our work, the known fact about opt in the two Wilber bounds were as such. So the alternation bound and the funnel bounds are known to be smaller than opt because they're low bounds, but we knew nothing about the relationship between them. And now we know a bit more. So first we know that for all sequences, the alternation bound is smaller than the funnel bound. And this proves points B. But also we know that there are some sequences for which the alternation bound is much smaller than the funnel bound. And this is by a log n factor, which happens to be tight, given some of the results. And this also means that the alternation bound is much smaller than opt itself, because we know that the funnel bound is at most opts. But whether the funnel is equal or not to opts, that remains open. So that the third part remains open. And on the way, we get, as a bonus, sort of, a nicer definition for funnel, because we used that in proving that the alternation bound was smaller than the funnel bound. And that new definition is related to what I call pinwheels. The name was suggested to us by an anonymous reviewer, and we were very thankful for it because it's a very fun name. So what's a pinwheel? A pinwheel is a quadruple PQRS of points that are in this configuration. So they are on opposite sides of a rectangle, and they must be in this relative order in terms of both x coordinates and y coordinates. That is, P must be to the right of R and Q must be below S. And in addition, very important, the interior of this rectangle must be empty. Like, it cannot contain any other point in the geometric view, in the plot of the sequence that we're considering. We named it, it's named a pinwheel because it sort of looks like a pinwheel, because you can draw points on each wing of the pinwheel, and the points will be at the right location. It was called a Z rectangle in the paper because we were much less inventive than the anonymous reviewer. What we can do with a pinwheel bound is define to define the pinwheel bound, which is just a number of pinwheels that we can observe in the plot of X. And one of the results in our paper is that the funnel is characterized by the pinwheel bound. That is, the funnel is up to constant equal to pinwheel bound plus or minus a linear term that no one cares about. And I'm going to sketch the idea of the proof. It's pretty visual, so it should be easy to understand. So first we have to prove that if the funnel bound is big, then the pinwheel bound is big. So if the funnel bound is big, we have to show that there exist many pinwheels in the plot of X. And for that, we're going to look at an example here on the left, where the funnel, like, there's many funnel points and they cross a lot. They cross the dividing line a lot. If that's the case, then we can find a few pinwheels in there. For example, this would be a pinwheel, but also this rectangle would be a pinwheel. And the more times you switch, the more rectangles like this you would find. And the proof of why those are pinwheels, it's not too complicated. It starts with the observation that since all of the points that we're considering, for example, this one, and this one, they're all funnel points, then by definition, the highlighted regions over here all need to be empty. So there's only those two small regions, A and B, that are left, and it's also fairly easy to argue that those must be empty by choosing the 3 points on the button carefully. So that's one side of it. The other side of it is to show that when there's many pinwheels in the plot of X, then the funnel bound must be large as well. And the key for this is to observe that if several pinwheels share the same top point, so if they share the same point here, then they must be in this specific configuration. Like they must always be in a sort of staircase pattern where the highest one is very wide, and as you get lower, it gets narrower. And this configuration ensures that there's going to be many points on either side of the dividing line for this specific axis. And those points must all be funnel points, simply because the pinwheels must be empty, and so in particular rectangles like this must also be empty. And so this means that according to the definition of the funnel bound, we're going to cross many times over the dividing line, and thus the funnel bound is going to increase as this happens. So what now? What do we do now that we have another characterization of the funnel bound? Well, first is a couple of consequences. The first is that, well, it's just a much nicer definition, which is neat in itself. The previous definition for the funnel was pretty complicated, so it's very useful that we just have to count this very simple geometric figure, which is a pinwheel. But also it means that the funnel bound is invariant to rotations and vertical flips, which was not known before. It's invariant to rotation simply because pinwheels are rotationally invariant, and it's also invariant to vertical flips because from the definition of funnel, it's pretty clear that it's invariant to horizontal flips. And if you're invariant to horizontal flips and 100 degrees rotations, you must also be invariant to vertical flips. And this is good news. Like, those invariant results are good news because opt also has those properties. So that means that a funnel has a chance to match opt exactly and to be tight. So in my opinion, this is the biggest open question in the domain, except of course for the dynamic optimality conjecture itself. So here's a reminder of the state of knowledge that we have for the two Wilber bonds and opt. And so the only thing that remains open is this, whether funnel matches opt. If that is true, I think it would be very neat first, because it would give a very simple definition to opt, which is usually defined as a minimum of many things. In order to define opt, if this were the case, then you would simply have to, again, count the number of pinwheels, which is a very cute geometric figure. But also, if we want to prove that splay trees are greedy, that they are dynamically optimal, we need to compare them to opt. And therefore, if funnel were to match opt, then it would be potentially very useful for comparing those algorithms to opt. Because instead of having to prove that splay trees is better than every other algorithm, you would just have to charge the cost of splay trees to the pinwheel in some way. And so that might make the proof much simpler, at least if splay trees is dynamically optimal. So that's all I have for today. If you want to learn more about the dynamic optimality conjecture, you can either read our paper or start by this very nice survey by Joy Nakono, which is called In Pursuit of the Dynamic Optimality Conjecture. Thank you very much for your attention, and have a nice day.